Pete. Hey, Pete,
Yeah.
can I borrow $2,800? Thanks.
What? That's almost 3 grand.
Pete, I already said thanks. It's pretty rude to go back on an offer after someone's thanked you.
But I didn't make you an offer.
Oh, okay. Sure you didn't.
Can we just back up a sec? What do you need all this money for?
Just a quick flight to Finland and back.
Finland? It costs $2,800 to fly round trip from the Bay Area to Finland?
Yeah, well, with a stopover in Paris. But I'm not going to charge you for all the chocolate and croissants I'm going to eat. That's on me. I mean, of course I'm including the cost of my one-day ticket to Disneyland Paris. I have to do something during my layover, right? I'm not just going to curl up on the floor of the airport and take a nap on my duffel bag for 6 hours, am I?
Disneyland? No, you know what? Forget about Disneyland. Forget about your little duffel bag. Why exactly do you think you're going to Finland?
Don't you read Newsweek?
I guess sometimes. Do you read it?
Me? Of course not. But they did publish an interesting article a couple weeks ago that's been making the rounds on the math boards.
An article? About what?
Get this. Apparently, a couple of hikers were out on what do they call it? That thing hikers go on?
A hike?
Yeah, a hike in Nuuksio National Park, just a bit northwest of Helsinki. And they came across this math problem tied to a tree.
All right. You're starting to pique my interest a little. Go on.
So they took a picture of it, right, and posted it online. And this problem has sparked some debate. There are some people who are calling it an unsolvable problem, but others are saying that it's infinitely solvable and that it has tons of solutions. Either way, don't you think this would be a pretty cool topic for a math club episode?
Well, I do, but why do you have to go all the way to Finland for us to do an episode about it?
Oh, well, the story happened in Finland. And that makes it a math story from Europe. And I've never been to Euro Disney.
Me neither, but
Well, then, it's very generous of you to offer to send me there on behalf of the show. You're an excellent co-host and a true friend, Peter Littig.
I never really offered. All right, we'll make this episode when you get back, but the math club owes me.
Merci, mon ami. Au revoir. Or, I mean, however they say goodbye in Finnish.
Finnish.
Oh, I'm already done.
Okay, Noah, so while you were booking a flight to Finland, I just got on the interwebs and typed in unsolvable Newsweek Finnish math problem, and I got the article that we needed.
Oh, well, was that as much fun as getting to go on Space Mountain in Paris?
I guess not, but it was a lot quicker. I'll tell you that. So I found this article on my Apple News app and it caught my eye about the unsolvability of this problem. And so I was expecting when I just read the headline that, oh, there's going to be some real big math problem that's under discussion here. And boy, was I pretty much not right about that.
No, you're right. It doesn't look like a very difficult or unsolvable problem once you get your eyes on it, does it?
No, but in fact, now that you bring it up, since your training in mathematics doesn't go quite as deep as mine, why don't you tell me what your pair of eyes saw when you first looked at this image and maybe take a moment to describe to our listeners what it looks like?
All right. So here's what the problem looks like. And we will also include a link to the article in our show notes so that listeners can go and take a look at it themselves if they'd like to. But it consists of 3 lines. And it's the type of problem that you've probably seen before online where it has different little pictograms and equations using them, and it sets up a few equalities, and then at the end it asks you what a different group of the same pictograms must add up to. So in this problem, the top row is soccer ball plus soccer ball plus soccer ball equals 3,000.
Okay, so right away, it's like kind of math, but also like a rebus, right? It looks like it's something not entirely mathematical.
That's correct. And since there are three soccer balls and they add up to 3,000, when I saw that, I assumed that each soccer ball was 1,000.
Okay, great. And what does the second line of this note tell us?
Well, the second line introduces a couple of new pictograms. First, it has a pair of skis plus another pair of skis plus a hockey stick, and that equals 22.
Okay, so this equation has a little bit more going on than the first one. It has two different pictograms in it, but it still establishes an equality, right? It's equal to 22.
Right. And then the bottom line poses the question, and it shows just one ski plus two times soccer ball plus hockey stick equals question mark. So we've already seen the soccer ball, the pair of skis, and the hockey stick. And now we're seeing a new equation that says one ski plus two times soccer ball plus hockey stick equals what?
Okay, so that last line is asking us to generate some final outcome, unlike the first two lines that are equations with a number provided on the right-hand side. That's not true for this last line. Is there anything else on this message aside from those three lines?
There is. At the very top, there's a Finnish word, which I'm going to completely butcher when I try to say it, but it looks to me like it is Maialman Mastari, and then a blank, like where you can fill something in. And in looking it up, Maialman Mastari is Finnish for world champions.
Okay, so my read on this right away is this is not presenting itself as a pure mathematics problem, right? This feels more like an escape room puzzle where you and your partners are desperately trying to beat some timer to get out of whatever room you're in. And then this thing shows up and it's clearly mathematical ish, if I may say that word, but it's definitely got something else going on. Like, there's a Finnish expression at the top of it about some kind of world champion. And then there's this weird thing I noticed with the bottom line where there's only one ski. Like the second line introduces the pair of skis, right? Pair of skis plus pair of skis plus hockey stick equals 22. And now in this last line, we've only got one ski. Like, where did the other ski go? you know? So we're obviously supposed to do something with it, but this is puzzly in nature. This is more, I would say, almost more puzzle than math at this point.
He's more machine now than man, twisted and evil.
Yeah, I think I agree with that. And I especially like your comparison to an escape room puzzle because I've done my fair share of those. And you're exactly right. There's something about an escape room puzzle that's not always super straightforward. You have to kind of have a little bit of an aha or figure something out before you can even actually solve those puzzles.
Yeah. And what I find also interesting about this entire presentation is the way it is sort of couched inside this Newsweek article. I mean, right off the bat, the title of the article is Unsolvable Math Problem Found Stuck to a Tree by Hiker Has People Baffled. Okay, so already just that alone hooked me in. I was like, all right, definitely I will front the $2,800 to get Noah to Finland so we can know what's going on with this mystery at the tree, right? And I really liked the use of the word baffled because being baffled is a sort of natural state for mathematicians. In fact, we kind of go out of our way looking for things that confuse and baffle us because that's where the mystery is. It's where the adventure begins. So the headline of the article really drew me in.
Yeah. Now, I have to admit, when I saw the problem, I didn't feel baffled. I felt like I had a toehold almost right away and starting to solve it. But then I thought, maybe I'm doing this wrong. If all of these people are baffled, what makes me think I've got some kind of solution that nobody else can find?
Well, you certainly solved the soccer ball real quick, right? Even if you're not thinking about mathematics in its proper sense, soccer ball plus soccer ball equals 3,000. I know soccer ball equals 1,000, right? Like that's pretty straightforward. But Tell me about the second equation. What were you thinking when you read it?
Well, it's kind of funny now when I think back to it because I saw pair of skis plus hockey stick equals 22. And my mind just immediately thought, oh, well, if the hockey stick is 2, the pair of skis plus the other pair of skis are 20. So each pair of skis are 10. And I looked at it and went, yeah, 10 plus 2 is 22. And then I patted myself on the back for the fact that I came up with the exact right numbers on my first guess.
Won't they be impressed? I am a genius.
Yeah. So how exactly is this baffling, right? Like you basically fall out of your chair and you've got the right answer. Done. Like not baffling.
Right, Pete. But then, like half a second later, I went, wait a second. There's nothing saying that all the skis have to add up to 20 and the hockey stick has to be the last 2. I mean, what if the hockey stick was 4, leaving 18? So each pair of skis is 9. Or what if the hockey stick was 6, leaving 16? So each pair of skis is 8. It seems like there's a lot of different answers that work here.
Yeah. And all of the answers that you've proposed so far are just positive whole numbers. Like, what if the skis happen to be equal to -1/2? And now you've got -1/2 plus -1/2, which is -1, plus hockey stick equals 22. Well, hockey stick must be 23 in that case. And there really are no other constraints on this problem at all. Like, those quantities could be irrational numbers, right? Maybe the hockey stick is 1 plus square root of 5 all divided by 2, right? Like there really is no additional context here. And yet somehow we're supposed to determine what 1 ski plus 2 soccer balls plus hockey stick is equal to. So now I think this is where that Finnish clue from the top of the message might come in handy.
The one that means world champion and then has a blank.
Yeah, and it's kind of my assumption in looking at this is whatever the answer is down at the bottom to ski plus 2 soccer balls plus hockey stick, whatever that's equal to, it's supposed to be the answer to this world champion, right? It says world champion underscore. Like there's a blank line where we're supposed to put an answer. And I think the mathematical answer we get from the bottom is supposed to make sense as world champion.
Yeah. And in fact, if you scroll down in the article, there are a lot of people who think that the answer is supposed to be 2007 because that was the year when Kimi Räikkönen, who's a national hero and Formula One legend, clinched the Formula One Drivers' Championship, which is something that a lot of Finnish sports fans are still incredibly proud of.
Yeah, exactly. And again, this all reinforces my sort of intuition about this is like an escape room puzzle, right? Like you're not going to take this to the halls of academia and, and knock on the door of, Professor Algebra and say, excuse me, professor. And then like, they're going to say, oh yeah, the answer is 2007. I mean, mathematically, and I want to dive into this now, there's a lot of interesting stuff going on here that has been wrapped up in people's sense of bafflement or their idea that this is either unsolvable or impossible. We can actually make quite a bit of sense of the mathematics if we just sort of step outside the context of the puzzle.
All right. And I'm assuming that maybe our first step here would be to get rid of the pictograms and rewrite these equations using standard variables.
Yeah, exactly. So if we did that, what would these equations be?
All right. Well, let's give these variables that we can remember. So let's use B for the ball. So B plus B plus B equals 3,000 or 3B equals 3,000.
To be or not to be? That is the question.
And then let's use P for each pair of skis and H for the hockey stick. So we have P plus H equals 22 or 2P plus H equals 22.
Right. So what we have just done is converted this pictographic representation into 2 linear equations. The first equation is 3B equals 3,000. The second equation is 2P plus H equals 22. And together they form something called a linear system. And within the realm of mathematics, specifically in the field of linear algebra, students spend a lot of time learning about linear systems and about how to solve them. So this problem would fit really nicely within the context of a very standard linear algebra class.
All right. So how would we proceed to solve it?
Well, we could start with the kind of follow your nose approach that you were taking when you first saw the puzzle.
Follow your nose. It always knows.
So you said, oh, 3 soccer balls equals 3,000. It's like 3b equals 3,000. I'll divide both sides of the equation by 3, and I get b equals 1,000. And I'm just going to kind of go and take each line by itself, if I can, and perform some algebraic operation on it. And in fact, this reminds me of the conversation that you and our friend Pete Mullen had in our We Love the Subs episode.
We love these subs!
You've got some equations. You're going to try to solve for variables and substitute them in somewhere else.
Right. I do remember doing that with Pete. And we talked a lot about systems of equations and how by using substitution, you can solve them.
Right. And now here we're being asked ultimately to answer the question, ski plus 2 soccer balls plus hockey stick equals what? So in fact, if we could figure out what a ski is equal to, we already know what a soccer ball is. So that's 2 times soccer ball, that's 2,000. And if we knew the hockey stick, we could substitute that value in, take the sum, and we would know what the answer is. But we don't have those other values yet. We don't know what ski is equal to, and we don't know what hockey stick is equal to.
That's right. And I'd like to pause here for a second to talk about something interesting I saw in the comments. And it's about the fact that we have a pair of skis in the second line, and then we have to figure out what does one ski mean in the third line. When I saw it, I assumed that one ski would be equal to half of a pair of skis. So for example, if a pair of skis was 10, one ski would be 5. But then I saw a comment that somebody made underneath the article where they said they were naturally assuming that this pair of skis stood for a 2-digit number since there are 2 identical skis. So they thought it must be 11 or 22 or a number like that. And I thought that was kind of interesting because even though I didn't choose to interpret it that way, it really is another bit that shows you how there's some ambiguity to this problem that makes it a little bit more of a puzzle than a math problem, like you were saying before.
Yeah, I mean, clearly what they mean in the second line is, hey, pair of skis, that is a quantity. You can think of it as a single variable. And now on the bottom line, when you have a ski all by itself, well, what does that mean? In the world of puzzles, who's to say? Maybe you really are supposed to think that one of those skis is a digit and put together, a pair of skis creates a double-digit number. But I think pretty clearly here, what's being asked of us is to take 1/2 whatever the value is for P. Now, clearly, this is a weirdo thing to do because if I have a variable quantity called W and I do half of it, I don't just call it U, right? It's not like, half of W is just U.
Obviously, half of W isn't U, it's V.
Right. Good point. But in this particular problem, we actually don't have enough information to just use a substitution method and ultimately figure out each quantity on its own. And that's because this linear system is under-specified.
Can you be any more specific?
And what that means is we have fewer equations, we have 2, than variables, of which we have 3. So this is the kind of observation and the kind of study that one does in linear algebra. You look at the number of equations in your system and you look at the number of variables that you have. And then there are various determinations that you can make based on the relationship of those 2 quantities.
Okay. And because we have fewer equations than we have variables, this is not a system we can solve with substitution.
Well, let's see what would happen if we did try to solve it by substitution. So when we look at the second equation, 2p plus h equals 22. If you're thinking about substitution, what's your next move?
Well, I'm going to probably try to isolate one of the variables. So I would say h equals 22 minus 2p. But I see what you're saying because the top equation only has b's in it. It's not going to help me any to isolate the h or the p because it's not like I can substitute it into the other equation.
Right. But you could try to substitute everything you've got so far down into the bottom expression, which is 1/2 p plus 2b plus h equals something. Let's go ahead and substitute what you just learned for h.
Okay, so then it would be 1/2 of P plus 2 times B, which is going to be 2000, plus 22 minus 2P equals what?
Right. And if we combine some of this and move things around, we end up with 2022 minus 3 halves P equals what? So we did as much substitution as we possibly can, and we see that we still need to know a value for P before we can get an honest to goodness number to come out of this expression.
I see what you mean. So what can we do to try to solve this?
Well, actually, you've already hinted at this. So, do you remember when you were looking at the second equation, you recognized that depending on what choice you made for the pair of skis, you had some freedom to choose a different value for the hockey stick and vice versa. You said, well, the hockey stick doesn't have to be 2. If it's equal to 6, then that would mean that the 2 pair of skis together would equal 16. So a single pair of skis would equal 8. You recognized that you have a degree of freedom in this problem. And that final substituted result that we got, namely 2022 minus 3 halves P, that is revealing that degree of freedom. P is unconstrained. It is truly a free variable. And by making different choices of that quantity, we do get a final answer that we could then use to pin down whatever this puzzle is looking for.
It's starting to sound almost like what we might have here is the equation of a line, right? Because we're kind of saying for whatever value of the skis I get, what's my value of the hockey stick going to be? When the skis are this, the hockey stick is that. When the skis are this other thing, the hockey stick is this other thing. And it's sort of going to plot out like a line, isn't it?
That's exactly what it is. It happens to be a line in the coordinate system that relates P, which is the pair of skis, to H, which is the hockey stick. And so to pin down an answer from 2022 minus 3 halves P, we better choose a value of P that solves that clue at the top of the puzzle. I think that's how we're supposed to figure out which of the infinitely many solutions is the correct one.
Went forward in time to see all the possible outcomes of the coming conflict.
How many did we win?
1.
So combining what we know about math with what we know about puzzles and what we learned about the Finnish race car driver, I think we can make a pretty safe bet that the intended answer here was 2007.
Right. And, if you're just looking at the initial expression, 2022 minus 3 halves P, then why not substitute a few choices in for P to see what you get? If P is 0, you get 2022. If P is 10, you get 2022 minus 15, which is 2007.
Wait, if P is 10, you get 2007?
That's right.
Which means I was right in my initial guess. The pair of skis are 10 each.
Which totally cracks me up, given the setup for this baffling, impossible mystery of a puzzle. You looked at the picture and you're like, oh, soccer ball is 1,000, skis are 10, hockey stick is 2. And that turned out to be the right answer.
I love it. I totally love it. Now, in this puzzle, we have the clue of the world champion bit at the top, sort of leading us in the right direction. But what if we didn't? What would we do in that situation? Or how would we picture this?
Yeah, I'm glad you asked about how one can picture these linear systems because we actually can get a lot of mileage out of understanding their geometry. So in the situation we currently have, each of our 2 equations has 3 unknowns.
Well, hold on a second, Pete. What do you mean each of the equations has 3 unknowns? The top equation only has soccer ball plus soccer ball plus soccer ball. There's only one unknown in that equation. It's the soccer ball.
Right. And so when we are combining 2 equations simultaneously, it's understood that all of the variables are always in play. And if they don't show up in a particular equation, we understand that that's because there's a coefficient of 0 in front of them.
So let me make sure I understand what you're saying. We could say that this top equation is actually 3 soccer ball plus 0 pairs of skis plus 0 hockey sticks equals 3,000.
Exactly.
And then the second line would be 2 pairs of skis plus hockey stick plus 0 soccer balls equals 22?
Yeah, that's right. And if we interpret that into the mathematical language, the first equation would be 3b plus 0p plus 0h equals 3000. And the bottom equation would be 0b plus 2p plus h equals 22.
All right, I got it.
Now, these are linear equations, and an equation involving 3 variables, when set equal to some constant term, like the equations we have here, geometrically, those equations represent planes in 3-dimensional space.
Meaning we're not just using the X and Y axis, but we're using X, Y, and Z.
Yeah, or in the language of our variable names, the B axis, the P axis, and the H axis. But really, it's X, Y, and Z that we're talking about.
Okay, got it.
Now, these planes are not the kind that you jumped on to get yourself to Finland. These are infinite, flat, 2-dimensional surfaces in space. Does that make sense?
Yeah, that makes sense. I can picture that. It would be kind of like if I had a flat piece of poster board that went off infinitely in every direction.
Right. Now, each of our equations is geometrically a plane of that sort. So we've got 2 planes in 3-dimensional space, and the linear system translates into the question, what does the intersection of these 2 planes look like? So I want to ask you, Noah, can you imagine what are the possible ways that 2 planes could be configured in 3-dimensional space? And then let's talk about what their intersections would look like in each case.
All right. Well, I can picture one example where the 2 planes are sort of parallel to each other and don't intersect at all. Kind of like if I put that piece of poster board down on the table, and then I have another piece of poster board that's just sort of floating 2 inches above it, but exactly parallel to it. They're never going to intersect. That's going to have no solutions.
Yeah. So geometrically, there's no intersection. It's empty. Algebraically, back in the land of equations, that simply means there is no solution. 2 equations, 3 unknowns, they just don't have a solution in common. So we have 0 solutions in that case.
All right. Now, another way I could see those 2 planes intersecting is, let's say, again, I have that first piece of poster board down on the table. I have that second one that's floating just above it, but now I'm going to rotate that one that's floating so it's perpendicular to the first one. Now it goes through it and makes an infinitely long line where they intersect.
Yeah, that's great. That's really good. So in that situation, the 2 planes intersect each other in a 1-dimensional line, which, as you pointed out, extends infinitely far in each of 2 directions. And there we would say there are infinitely many solutions. Every point on that line gives a different solution to both of the equations. And that actually happens to be the case that we're in here with the soccer ball problem.
All right. But I can also picture one more way, I think. I'm not sure. But what if I take that first piece of poster board and put it down on the table, and then I take that second piece of poster board and basically put it in the exact same place, the exact same orientation, so that every point on the second plane is touching a point on the first one? Does that count as 2 planes, or is that really just 1 plane?
I guess geometrically, I would sort of say, yeah, it's probably the intersection of 2 identical planes is that common plane. Algebraically, though, we could represent that by 2 equations which are giving the same information. So here's a simple example. 3x equals 3000 and x equals 1000. 2 different equations, but they give exactly the same information. And so it is possible to have 2 planes which are identically the same.
And then in that case, it seems like we would have infinitely many solutions again.
Exactly right. Again, infinitely many solutions, a bigger kind of infinity, if you will. And there is a way in the context of linear algebra to make sense of the different sizes of those 2 infinities. And we've already been using that language. The line has 1 dimension to it. Even though it would be a line in 3-dimensional space, the line itself is 1-dimensional and the planes are 2-dimensional. If you were standing on one of those planes, you could walk around in one of 2 different independent directions. So there is a way to quantify the difference, but in both cases, infinitely many solutions.
That makes sense.
All right. So Noah, we've talked about three situations. We've got zero solutions or infinitely many solutions. Can you think of a geometric configuration that would pin everything down to a single solution?
Well, for that to happen, I would have to be able to take the two planes and have them intersect at only one point. And I'm trying to picture it. I can't picture a way that they would intersect like that. Am I just not thinking of it, or are you tricking me?
It's not a trick, but it's not possible to do with just two planes. That's a hint.
Oh, I see. If I add a third plane to the mix, now it can come through kind of at a skewed angle to the other two and intersect that line at just one point.
That's exactly right. Each pair of planes would intersect in a line, but when taken all together, there's just a single point in common. And so earlier I said that this system is underdetermined or underspecified. It's because two equations with three unknowns can never pin down a unique solution. You need to have at least the same number of equations as you have unknowns.
And I think when you say two equations with three unknowns can never have just a single solution, that's the algebraic description of what I'm picturing geometrically as two planes can never intersect at just one point.
In three-dimensional space, that's absolutely right. If we allow ourselves to work in higher dimensional spaces, then it would be possible to get two-dimensional planes to intersect at a single point. But linear systems in higher dimensions involve geometric gadgets called hyperplanes. So they're bigger than ordinary planes are. It's kind of like the same way as, the difference. If you take a line in the plane and compare that to a plane in three-dimensional space, well, keep bumping all the dimensions up, and now you'll get an idea of what these hyperplanes are. So in essence, though, what you just said is exactly right. If you don't have enough constraints, i.e. equations, you just cannot pin things down to a single solution.
That's pretty cool, Pete. I like that. So aside from solving puzzles that we find tied to trees while we're hiking through national parks in Finland, what kind of real world applications does this kind of math have?
Well, actually, there are tons.
Like the puzzle, there's infinitely many applications?
I think you're onto something there. Yeah. And in fact, many years ago when I was teaching linear algebra, I came across a quote on the internet that has still stuck with me because it's both ridiculous and also like absolutely true at the same time. And the quote goes like this: 98% of all mathematics is linear algebra, which like clearly can't be true, but yet there's something about it that it's so true because it's really everywhere. So there are applications in electronic circuit design. There are applications in chemistry with balancing systems of chemical equations. There are applications in finance, in economics, and believe it or not, in urban planning.
Urban planning? How can linear algebra help there?
Well, let's suppose we were interested in the timing of traffic lights. Now, maybe you've driven down an arterial route in a city and have thought to yourself, wow, these lights are just not timed very well. I have to keep stopping because the light is always turning red at just the wrong time. Or let's suppose there are too many cars coming down a particular road and you'd like to find ways to divert them by, say, creating a new intersection and adding a new road. Well, this kind of mathematical model could help you in both of those situations.
Using the kind of math we used in the soccer ball problem? How?
I'll tell you what, I have a pretty cool example in mind, but it would definitely be easier if I could show you and our listeners too what I was talking about. So how about we wrap this episode up now, and then we put out a video bonus to explain the traffic flow application in the next couple of days.
Sounds good, Pete. And thanks for yet another fascinating conversation. I really learned a lot talking with you about this puzzle and linear algebra.
For the low price of $2,800, it was worth it, my friend.
Now, before we go, can you let folks know where they can reach out to us if they want to ask a question, or suggest topics for future episodes?
You bet. Math Club, we would love to hear from you. Why not drop by our SpeakPipe page and leave us a voice message? The URL is speakpipe.com/mathclubpodcast. As always, you can find us on X, formerly known as Twitter. Our handle is @mathclubpodcast, and our email address is mathclubpodcast@gmail.com.
And here's something exciting. We have a new place where you can find us. We also now have a YouTube channel. Guess what it's called? That's right, @Math Club Podcast. All of our episodes are also available there, and we would love to see you drop by. Oh, Pete, I gotta run. My Euro Disney Fast Pass is flashing and telling me it's my turn to get on Big Thunder Mountain.
Wait, you're still in Paris? Did you even go to Finland?
We'll see you next time, everybody. Bye-bye.
Au revoir.